Have you ever wondered where stars come from? Well, let's embark on a journey to the heart of a nebula, a vast cloud of gas and dust in the far reaches of space. It's here that the magic begins. Over millions of years, the nebula's gravity pulls its matter inward, forming a dense core. This is the birth of a protostar. Now imagine this protostar growing denser and hotter, its gravity pulling in more matter from the surrounding nebula. This process of gravitational collapse continues until the core of the protostar is so hot and dense that nuclear fusion begins. Hydrogen atoms meld together to form helium, releasing an incredible amount of energy in the process. This energy pushes outward, countering the inward pull of gravity, and voila, a main sequence star is born. And thus, a star takes its place in the universe, shining brightly across the cosmos. A star, now born, embarks on a long journey of burning brightly. This journey, often spanning billions of years, sees the star in its main sequence phase. Here, a delicate dance unfolds at the star's core as it burns hydrogen into helium, releasing energy in the form of light and heat. This energy radiates outwards, creating a pressure that pushes against the overwhelming force of gravity pulling everything inward. This intricate balance between outward radiation pressure and inward gravitational pull is what keeps the star stable, allowing it to shine brightly in the cosmos. Yet this phase is not eternal. As the star exhausts its hydrogen supply, the delicate equilibrium begins to falter. The star, in its struggle against gravity, starts to contract and heat up, paving the way for the next stage of its life. But as we know, nothing lasts forever, not even the life of a star. So what happens when a star exhausts its nuclear fuel? Well, the answer to that takes us on a breathtaking journey through the final stages of a star's life. As the star burns through its nuclear fuel, it swells into a red giant. This phase showcases the star at its most captivating, a giant orb of glowing gas that dwarfs its former size. But this grand spectacle is a harbinger of the star's impending demise. As the star continues to burn its fuel, a dramatic transformation occurs at its core. No longer able to sustain nuclear fusion, the core begins to contract under its own immense gravity. This process, known as core collapse, is a pivotal moment in the life cycle of a star. It's the point of no return, where the star's fate is sealed. The core's contraction intensifies, reaching a fever pitch as it implodes in on itself. The pressure and temperature skyrocket, triggering a cataclysmic rebound effect. This rebound, like a cosmic spring uncoiling, unleashes an unimaginable amount of energy outwards. The star's outer layers, once peacefully drifting in the red giant phase, are violently cast off into the cosmos. This outward energy, a shockwave of epic proportions, rips through the star, tearing it apart from the inside out. This isn't a slow, languishing death. It's a spectacular, explosive finale that outshines entire galaxies. But the star's end is not a mere spectacle. It's a transformative process, a cosmic forge where elements heavier than iron are created. These elements, flung out into the universe by the supernova's shockwave, seed the cosmos with the building blocks for new stars, planets, and possibly life. And so, in the star's final act, it gives birth to something new, something extraordinary. In a blinding flash of energy, a supernova is born. What makes a supernova so incredibly powerful? This question takes us to the heart of one of the most cataclysmic events in the cosmos. Supernovae, the explosive deaths of stars, are exceptional demonstrations of cosmic power and transformation. There are two main types of supernovae, each with distinct characteristics and mechanisms of explosion. Type Ia supernovae occur in binary star systems, where two stars orbit each other. One of these stars is a white dwarf, the dense remnants of a star that has exhausted its nuclear fuel. When this white dwarf siphons off too much matter from its companion, it can no longer support its own weight. The result is a thermonuclear detonation, a runaway nuclear reaction that rips the star apart in a brilliant explosion. On the other hand, Type 2 supernovae are the explosive deaths of single, massive stars. When these stars exhaust their nuclear fuel, their cores collapse under their own immense gravity. This core collapse triggers a shockwave that blasts the outer layers of the star into space, creating a spectacular supernova. The forces unleashed in these explosions are nearly unfathomable. Imagine an energy output equivalent to the combined light of 100 billion stars, all released in a single moment. That's the power of a supernova. But these cataclysmic events do more than just dazzle the eye. Supernovae play a critical role in the cosmic cycle of death and rebirth. The explosions scatter the elements forged in the hearts of stars across the cosmos. These elements, from oxygen to iron, are the building blocks of planets, of life, and of us. In a very real sense, we are children of the stars, born from the ashes of stellar death. So when we ask, what makes a supernova so incredibly powerful? We're also asking about our own origins and the intricate web of cosmic connections that bind us to the universe. Supernovae, in their explosive deaths, give birth to elements that make up everything around us. But what happens after a supernova explosion? Hold on to your seats because we're about to embark on a cosmic journey through the aftermath of a supernova. As the dust settles, the beauty of destruction unfolds, revealing a cosmic symphony of creation, evolution, and transformation. When a star explodes into a supernova, it doesn't just signal an end, but a beginning. The explosion seeds the universe with heavy elements that are not naturally produced anywhere else. We're talking about elements like gold, silver, and uranium. Yes, the gold in your jewelry, the silver in your cutlery, even the uranium powering nuclear reactors, all are stardust, born from the heart of a dying star. But the impact of supernovae doesn't end there. These explosions also trigger the birth of new stars and planetary systems. When a supernova detonates, it disperses its enriched guts into the surrounding space, creating dense clouds of gas and dust. Over time, gravity pulls these clouds together, forming new stars and planets in a process that could take millions of years. This means that every star you see in the night sky, every planet in our solar system, even our own Earth, owes its existence to the explosive death of a star. The role of supernovae in galactic evolution is profound. As they explode, they shape the structure and dynamics of galaxies, stirring up the interstellar medium, triggering star formation, and even influencing the growth of supermassive black holes at the heart of galaxies. So, next time you look up at the night sky, remember this. Each twinkling star is part of an extraordinary cycle of cosmic life and death, a cycle driven by the cataclysmic power of supernovae. Each supernova is a creator and a destroyer, a cosmic phoenix rising from the ashes of its predecessor. Supernovae, in their destruction, create the building blocks for new stars and planets. How do supernovae explosions help us understand the universe? This question has intrigued astronomers and scientists for decades, and the answers they've found are nothing short of awe-inspiring. Supernovae are not just celestial fireworks. They're cosmic laboratories where the laws of physics are pushed to their extreme. They allow us to probe the most elusive phenomena in the cosmos, like dark energy, the mysterious force that's accelerating the expansion of the universe. By studying the light from type Ia supernovae, which explode with a consistent brightness, astrophysicists have been able to measure how quickly the universe is expanding. This has led to the groundbreaking discovery that the universe's expansion is accelerating, not slowing down as previously thought. It's as if you threw an apple into the air expecting it to fall, but instead, it zoomed off into the sky. Not only do supernovae help us understand the grand scale of the universe, but they also shed light on the smallest of particles. Neutrinos, nearly massless particles that rarely interact with matter, are released in vast numbers during a supernova. Catching these elusive particles can give us a unique insight into the fundamental workings of the universe. Supernovae also play a crucial role in cosmic evolution. They explode with such force that they can trigger the birth of new stars and planetary systems. They seed the universe with heavy elements, the building blocks of planets and life itself. Every atom in our bodies, from the calcium in our bones to the iron in our blood, was once forged in the heart of a dying star. Through the lens of a supernova, we see the universe's past, present, and future unfold. From the ashes of supernova, new stars are born. And with each new generation of stars, the universe evolves, creating the cosmic landscape we see today. In the grand theater of the cosmos, supernovae are the dramatic act that sets the stage for the next scene, shaping the story of the universe as it unfolds.